So hi, I'm David Bell. I'm a senior staff software engineer at Uber. This is my partner, Ronak Jain. He's a staff software engineer at Uber. Today we're going to be talking about, not too creatively titled, like securing every bit at Uber. So we're going to go over, what was the problem? Why was this problem hard? Like, why are you even listening to this talk? Our approach to solving the problem, and then some of the performance numbers we've gotten, as well as some of the challenges we've overcome in developing this. So first off, for the problem, what do we want at Uber? We basically want to have a zero trust architecture. I won't go into what zero trust architecture is too much, but it's basically, we want to prevent bad people from doing bad things within our network and affecting our customers, like exfiltrating data, compromising services, things of that bad stuff. Through that, we want to assume that there's no implicit trust between workloads. And we want to establish basically a baseline of encryption, authentication, authorization, and auditability between every interaction between workloads. And when I say workloads, I mean things like services, databases, batch jobs, things of that nature. And so the reality is, we had some of this stuff in some of the places, some of the time everywhere. So for example, in our batch ecosystem, we had heavy usage of Kerberos, but effectively none of that outside of batch. We had some homegrown authentication authorization solutions and inconsistent deployment of encryption transit, kind of based on what was the criticality of that service or that interaction. And because of this, we didn't really have any kind of centralized auditing. Like, we're trying to integrate many different systems together to figure out what of these controls were in place at what time. And so our goal was we wanted to raise the baseline of encryption, authentication, and authorization at Uber, and basically apply something 100% across everything at Uber. And so why was this hard? So first off, there's scale. We have hundreds of thousands of machines running millions of containerized workloads. We have hundreds of terabits of traffic, over billions of connections. And in our L7 layer, we are supporting hundreds of millions of RPS requests per second that we also have to deal with when we're also applying encryption, auth and auth. For performance, we have service owners that have dialed in their SLAs around throughput, latency, availability, and so we have some wiggle room, but not a ton. So when we're introducing whatever we do, we need to make sure that we're not going to suddenly trigger a bunch of alerts because we've regressed their SLAs. We also have correctness concerns. If there's any behavior you have in your network, somebody's going to take a dependency on that. And so we had to be very careful that we weren't breaking anybody that was doing something kind of at the edge or odd. And lastly, for reliability, like I mentioned, our goal, that's kind of a business goal. We want to have this secure baseline. But for service owners, they just want to make sure they hit their SLOs. And so if in the process of delivering this, we start to impact service availability, that's going to create a lot of noise for us. Those people are going to complain. That's going to slow us down and make it harder for us to actually achieve our goals. And stop me if you've heard this. So we have many different applications on the order of thousands of stateless services, stateful databases, and tens of thousands of batch jobs across many different frameworks. So we have a lot of Go and Java, but also Python in the data stack. We have open source frameworks being used like Yarn and Spark, open source databases like Redis, MySQL, but also a bunch of custom stuff. And kind of the most interesting is we actually had 4 different orchestrators. So only one of them being Kubernetes. We're fixing that. But you also just had 4 different ways of deploying things, and some of them using Kubernetes, some of them using Containerd, some of them doing Docker run. And so having kind of any consistency in the data plane was really challenging. And also, we don't have network namespaces, at least not yet. Everything's host networking, using dynamically allocated ports. And so a lot of the niceties that you have in the ecosystem just weren't available to us. And so for our approach, I kind of set out with these 3 tenets. So first, we want to target the lowest common denominator and drive that to 100%. And so despite all those different languages and frameworks and implementations, everything used TCP, so let's target that. And maybe we don't get all the niceties we want, like per request authorization, but we could at least get like connection level. And so you also see this in like Istio with ztunnel, being able to target a very common base layer. We also made sure we didn't rebuild what we didn't have to, reusing what we knew worked. So for example, we have a lot of experience running Envoy on our edge, and we're doing a migration internally from our homegrown L7 load balancer to Envoy. And so we had a lot of experience there with Envoy. We built out a lot of infrastructure for it, and we knew we could hit the ground running if we were able to baseline on that. Similarly for using Spire for certificates, as well as a lot of the integrations we had for how do we associate identity with containers in this kind of multi-orchestrator world. And lastly, graceful degradation. This thing didn't exist before we built it and deployed it, and so we should be easily able to kind of degrade back to the state of the world prior to that. So if we have any issues with deployment, we have any performance concerns, even like a hint that something's going wrong, we should be able to ideally automatically, autonomously, just revert back to the default state. So our approach ended up using a combination of Linux kernel primitives, eBPF, and NF tables to redirect traffic over an Envoy proxy. So Envoy does form the base of our kind of encrypted, authenticated, authorized data plane. So with Envoy, we got basically batteries included for MTLS, RBAC. We use proxy protocol, which I'll talk about in the next slide, as well as original destination dynamic forwarding. And basically using just features that come out of the box configured in Envoy. And for things that didn't exist in Envoy, we were able to use Envoy's custom plugin filter system to easily extend it. So we can do like that connection attestation and identify when we redirect a connection to the proxy, like what is actually behind that connection? What is the identity of that? We run Envoy using a Go nanny process. And this is actually something we'd originally built for our L7 internal proxy layer that we're migrating to. But because effectively we can create different brains where we have the kind of the L4 secure data plane brain, the L7 routing data plane, we're able to share a lot of the logic between that. And so even though they'd been working on that first, we were able to repurpose it for our use case. And now we've actually contributed back a lot of operational tooling around things like restarts, monitoring, debugging. So now they're able to use that for their L7 internal data plane. And so for traffic redirection, I think I mentioned we're using NF tables and eBPF. So when a container launches, we have labels on that container that allow us to determine whether that should be onboarded to the system. And then we'll configure that in NF tables to redirect its packets to the proxy. And then using a bit of eBPF to propagate some state on the connection that we can look up in the proxy. And then lastly, to solve that multi-orchestrator problem, we've ended up wrapping runc. So for those that aren't aware, you have, say, Docker, below that you have container D, below that you have runc, and that's kind of the basis of where containers actually get launched. So we took a page out of some other playbooks, like I think AWS did this with something they called like Hotdog. Where they basically wrap runc to inject additional hooks into the container launch. So we're able to use that to set up the attestation information for a container. But we're also able to hook in right before we launch the container process and actually do an end-to-end check to make sure that everything's configured on the host. So all of this stuff is happening asynchronously, like a container gets launched. We update the Envoy with information about how to bind the certificates and policies for that container. And we want to make sure that's all configured before we actually let that container launch the entry point and start actually interacting with the proxy. On the wire, we're just using one-to-one TCP connections with MTLS on top, then using proxy protocol on top of that to signal the original destination. We did look at alternatives for this using like H2 Connect, which I think is using ztunnel. We opted not to use that. One, at the time, we found some crashes in it, and we were trying to move fast. But also, we were a bit concerned about the overhead of having the HTTP stack involved on top of everything else. And because we are very cost sensitive, we were very concerned about that. Additionally, we're also concerned about packet loss. So at Uber, we operate multi-region, but also multi-provider. So right now, we're in a combination of on-premises data centers, Google Cloud, and OCI. And while we generally find that packet loss is pretty minimal within the provider, we do find that we have packet loss events between providers, between regions. And so we were concerned about head-of-line blocking on shared H2 connections. That does mean, and Ronak's going to go into this later, that we are kind of churning more TLS sessions and connections than we would otherwise. It also made it a little bit easier to integrate it into our L7 proxy layer. So not only are we doing this for the P2P connections, but we've also integrated this protocol into the outbound side of our L7 proxies. So we're actually able to do that authentication, authorization kind of on behalf of the callers. So rather than having our L7 proxy say like, hi, I'm L7 proxy, I want to connect to the foobar service, we can actually do it on behalf of the client. And then for deployments, we're just using the standard Envoy, live migration, and traffic drains. So we're able to incrementally drain connections after we've established the new proxy and have clients gracefully reconnect. We did actually fix an issue with idle connections where we found that while established connections will get drained normally throughout that kind of drain period, idle connections, because they weren't triggering events, were actually getting drained at the very end, which caused some issues for some workloads where we basically have like a big thundering herd of idle connections that they were using for quorum get drained at the end of the drain period, and so we resolved that. And then lastly, we're also using proxy protocol to do extensions. So for example, we have quality of service classification, where we basically down prioritize bulk traffic for batch jobs in our network over default. And so we're able to propagate that over the proxy using PPV2. For graceful degradation, we basically decided to be able to fail open and gracefully degrade at every point in the stack. So if we're not able to retrieve authorization policies, just let the traffic through, log the decision, and audit later. If we're not able to bind that identity because we can't get a certificate or because something's not working on the machine, we've modeled unauthenticated as a first-class identity in the system. So just do authorization with unauthenticated, log which machine that's on, let the traffic through. And then if the proxy's failing itself, whether it's overloaded, crashed, or something about how we're doing the traffic redirection isn't actually working, again, just fail open, disable all the traffic redirection. And so as part of this, we have some signals where we run a self-check on every machine that is actually continuously testing the proxy to make sure that it's responding and that we can send data end-to-end through the proxy on both the outbound side as well as the inbound. And we also, on the outbound side, if we detect that the destination proxy, for whatever reason we can't connect to it, we also do a custom fallback where we do plain text TCP direct to the destination application. And so that ensures that even if the destination's not running, we still attempt to establish the connection and maintain service availability. And that's also nice because then it makes it really easy for us to kind of do like incident mitigation. We can always kind of disable traffic redirection anywhere in the fleet. We can basically shut down any proxy, and generally the rest of the fleet will adapt to that and reestablish connections. So then for how we brought this to production, so we've been working on this for the better part of 2 years now. And so basically end of 2023, beginning of 2024, we did a kind of proof of concept, which again, Envoy was very helpful for. We were able to get up and running in about a week. And then after 3 months, we kind of put together a very minimally viable version of this, basically none of the productionalization. Basically, you put a workload on the machine, it gets put over the proxy, and we started testing workloads immediately, especially in our storage and batch ecosystem, because there we considered they'd be the most sensitive to performance, and also the ones with the most oddities. Generally for our stateless traffic, we know they can tolerate more latency, and also are more tolerant of connection resets. And so this gave us a lot of signal. We were able to integrate and add features that turned out we needed well before we actually had anything running in production. End of 2023, beginning of 2024, we had built up that production stack, and we started by onboarding somewhere between about 0.5% and 1% of all workloads at Uber, making sure that they were representative. So not just running kind of the junky, staging services that nobody really cares about, actually getting real, for us, tier 1 workloads, so the things that actually run the business. And we started doing that pretty much in February of last year, even before we'd done large-scale testing. And that ensured that we started to get production experience very early. And so that meant that we were able to build up our operational experience, set up runbooks, really debug our operational excellence. Once we got past that point, we decided to go very big. Because while we knew this kind of worked for the things we tested, we kind of assumed that there were some oddities out there somewhere, and the only way we were going to catch them was by putting them on the proxy. And so at Uber, like I assume at many companies, like we run multi-zone, multi-region, and we're generally pretty good about being able to fail away from a zone. So we have centralized controls to be able to drain traffic from a zone and drain it back. And so we opted to do a series of full zone tests where we drain a zone, onboard it over a few minutes, and then run it for about 30 minutes at a time. And so this allowed us to get a lot of information about how this thing performed at scale very quickly, while also being able to bound our worst case. Because we always knew if we blew up this zone, well, we have about a dozen more, we can just drain from this one and still be okay. And so then this influenced kind of, some of the work that Ronak did and some of the performance challenges and how we solved them. And so once we'd done that, we kind of demonstrated that this thing worked, at zone scale, worked at peak traffic, and so really at that point we kind of demonstrated this thing worked. We just had to show that it was stable over time. And so then we were able to, at the end of last year, do a rollout over a period of about 4 months. Now in that rollout, we did have people have concerns because with any rollout, any issue suddenly becomes, like, did you cause it? And so our methodology was, don't try and debug in the moment, roll back, analyze, demonstrate that you weren't the problem, or in the rare cases we were. But make sure that we preserve service availability at all costs. The result of that was that generally the rest of Uber had a lot of trust that we weren't going to break them. I think one of the big concerns up front was we were going to prioritize security, and then kind of all the way down here, availability and performance. And again, as I mentioned on that second slide, availability and performance is what they really care about. They want security, but they don't want to sacrifice that. And so because we demonstrated that we really cared about their performance and availability, and that we weren't going to regress them just for security, that gave us a lot of leeway and a lot of trust to be able to deliver very quickly. So where are we now? So onboarding, we have stateless and stateful basically fully onboarded. There's like 1 or 2 exceptional cases that we're working through, but all new workloads are enabled by default. For batch, we're about halfway done. We're sort of working through our different frameworks and ecosystems and getting them incrementally onboarded. We also need to make that quality of service feature work before we could onboard them. And they're just kind of slowly incrementally rolling out. And for scale, so right now we have billions of established connections, tens of millions of new connections per second across our fleet. And about 40% of all network traffic within Uber is now on the platform, where that kind of 60% is basically those batch jobs, which isn't too surprising. They're the ones that are kind of driving a lot of bits. In terms of availability, we're about 5 nines of uptime. Generally, where we see unavailability is host crashes and kind of noisy batch workloads that decide that they're going to drive the machine to 100% utilization. And so while we're unavailable, not much else is available on that machine either. And we see about 0.5% of connection fallbacks. And that's actually because generally we find that services have stale topology, so they're trying to connect to something that no longer is running. We still try that connection anyways. So yeah, now I'm going to hand it over to Ronak to go over performance and challenges.
All right, thanks, David. So just going to be talking about performance challenges and how we scaled. Secure proxy is what we call Envoy. So this slide shows about the single host performance that we see on our fleet. We handle about 10K connections on an average and about 300 connections on the biggest machines that we have. These are large fan-out services or services that are talking to like large clusters in terms of topology. And then the rate of connections on these machines could be around 3,000 on the bigger ones. I mean, we've also seen worse, about 8,000 connections per second, unique sessions that's being created to different endpoints. Throughput-wise, since we don't have batch onboarded fully yet, the stateless traffic is mostly RPC, high number of RPCs, but less number of bytes in those. So peak average is around 300 Mbps, and the biggest we've seen is like 4 gigs. The reason why I'm going over this is we're just trying to set the baseline of why we started seeing performance issues after we started onboarding some performance and latency-sensitive workloads. Before we do that, just a quick background on how Envoy works. So there's the main thread, which is the control plane of Envoy, handles XGS, endpoints. You receive admin requests, health checks, metrics, everything is coming on main thread. And then there are worker threads, which actually manage the connection lifecycle, which is essentially the data plane of Envoy. And one nice thing is here, it's isolated, shared nothing architecture. Every worker thread has its own listeners, own set of connections. They're not sharing anything. So you have listener filters, network filters, clusters on a very high level, and each of those are like accepting connections, processing I/O events, and then also process the dispatched tasks from main thread. I mean, if we squeeze that down and then just look at it in terms of worker thread, you have a bunch of events, and there's an event loop that's continuously polling the events and processing those. And you see a bunch of events here. One is you have I/O events on connection 1, connection 2, and there are some events called new connections that I represent here. Those are essentially connections that we receive from downstream that needs to be proxied upstream. And when you try to proxy it upstream, you need to set up TLS state on those connections. That is TLS handshake, proxy protocol, and then finally that's ready for transferring data. So when you have like a large number of events, most of I/O events are not expensive. When we benchmark, we see those around 10 microseconds or less. So you are churning through events very fast, and overall you see a very stable latency in Envoy. That is, even if you are accepting connections, reading and writing data, you can actually produce very good throughput with Envoy. We see about 15 gigs of throughput per core, and multi-core is much better, of course. But then there's this one interesting thing in the event loop, which is TLS connections. TLS connections have special load to them. That is, they are CPU intensive. It's essentially the asymmetric algorithms that we use during handshakes that is not hardware accelerated. So you see a new socket, a new connection that needs TLS can take about 1 millisecond of your CPU time. And we've done this benchmark across x86 and a few other processors, but 1 millisecond is what an average time that we've seen across different SKUs. So let's look at an event loop where you have hundreds of connections that are blocking. It's again head of the line blocking, where you have hundreds of connections that need to be processed with TLS handshake, and then there are I/O events behind those. So before you get to the I/O events, that is RPC request or RPC responses that they're holding, you have to finish these entire connection handling. So while we process those connections fast enough, the latency, the CPU time that we spent on those connections is going to get added to the latency that request and response are going to see. So this is what actually started happening in production, where we would see random P99 increase for especially the latency sensitive applications. Generally, stateless and traffic is not that sensitive, but when it comes to Redis and calls that are going to memcached or like geostore, those are like super sensitive in Uber. So as soon as you do 100 milliseconds time on processing new connections, the existing RPCs time out, they start retrying, and some of those timeouts in gRPCs cancel the stream, whereas HTTP1 is close the connection, open a new connection. So eventually we would start seeing a loop where you have slow down the existing RPCs, you have more connections that are coming in, and then that starts thrashing the proxy, basically. Two cases where we see this is fan-in, where you have Redis clients that discover a new Redis node, and they start sending traffic to this new Redis node. So thousands of connections coming in to one single node. And fan-out, where one single application launches, boots up, and then starts connecting to all the Redis nodes, back in databases and others. So we tried a bunch of things. First, we set the standard thing, rate limits on each connection, each client, each server. What rate limits did was had hard failures on connections. So if application starting up, it cannot connect to Redis, they crash loop. And this generally very sensitive on startups. And then we tried CPU overload protection, where once you reach certain percentage of CPU, you stop accepting connections, start closing connections. But this was too reactive. By the time we started reacting, the loop was already full, and then the latency started kicking in. The next thing that we tried was reduce the number of accepts per loop. This was nice. It worked up for a bit. The only thing was, instead of queuing up connections in the loop, we started queuing connections in the kernel accept queue. So the kernel accept queue started overflowing. SYN drops are more expensive, take 1 second for retries. So and there's no ability for us to apply LIFO or any better approach on these. So to solve this, we built adaptive queuing and dispatching within Envoy. So queue holds a set of connections that we receive from listeners into a DQ, and then we smoothly start spreading these connections in the loop. That is 5 connections every 10 milliseconds or 20 milliseconds based on what the space on usage on that machine looks like. And then once we start hitting certain threshold, we switch from FIFO processing to LIFO. So we have higher chance of successful establishment. So in reality, it's more about start accepting connections in the DQ, and then batch those accepted connections, and then leave space for I/O events. So this is what we started doing. So before queuing, I won't go into too much of details here, but we had, as soon as the number of connections picked up, the number of RPCs and the throughput on that proxy used to crash down pretty hard. Latency used to jump to 500 milliseconds, and immediate drop in success rate as well. So after we built queuing, we had consistent success rate and latency improvement across the fleet. So far, it's been working really well. Due to time constraints, I'm going to jump ahead. And then the next challenge was with session reuse, where you all know there's zero RTT session reuse in TLS. You get a session ticket from server, and you can reuse that ticket to reach the upstream. Since we use shared nothing architecture in our fleet, where you have user service instance A, instance B, instance C, all of these use unique certs, and they don't share session ticket keys. So when Envoy tries reaching to one of the destinations, that is user service, it gets a ticket back, handed back to that. And the next time application needs to reach user service B, you send the ticket in, but the ticket is rejected because we do not have, the session key does not match the session key that instance A shares. So, which is why we started, we fixed this in the TLS transport, where session key now starts caching keys by upstream endpoints. So if you have 10 endpoints, we would have tickets associated with each of those endpoints. And overall, we started seeing much better session reuse with Envoy, about 30% or 400K connections per second in the fleet. We also use original test to. The setup is you have listeners, original test, and generally you have high fan out. That is, you reach out to tens of thousands of connections. So the thing with original test is every endpoint that gets added is sent to main thread, and then main thread needs to process that and also spread it to all the worker threads. Essentially, we started hitting a bottleneck where original test starts queuing too many of these events and starts blocking main thread. And then that starts failing our health checks and overall crashes the proxy for us. So we added batching support in original test, so now we have thousands of events batched together, so it doesn't take down main thread overall. And original source, we also use original source filter. One of the things that it does is on the upstream connection, it copies the source address that we see in downstream using bind syscall. But then when you do bind syscall, the source port, that ephemeral port that's allocated by kernel, is also removed from the reuse. So we, in production, we started hitting issues where after 25K connections, all the services started seeing out of ephemeral port. That is exhaustion, basically. So the solution was to add a socket option, IP bind address no port. So kernel ignores the port from reservation and just uses the address. So these were like quick walkthrough of the performance challenges that we saw. Just jump to the questions if you have any.
Of course, there's somebody at the back. I have seen you.
I do have some fairly in-depth questions about how you got started with injecting the proxies everywhere. Would you be around to talk after this? Because I don't want to take up everybody's time. I'm aware time is sensitive.
Yeah, sure.
Thank you.
We're here all week.
Yeah, thanks. So there's a 10-minute break between every talk in the schedule. The idea with that is that this is to allow folks to get up and maybe go to a different room if they want to see a different talk. Obviously, we know you would never want to leave Envoy calm. This is the best content. So I think what I'm going to do is probably just let folks run into that 10 minutes and do Q&A in that 10 minutes. If you do obviously want to go to another talk, if you could just get up quietly, I guess, and just make your way out. I think it's better than us just stopping for 10 minutes and all playing on our phones when we could be hearing stuff like this. But yeah, do feel free, obviously, to move between the rooms. But I think we'll use the space up. We do have to keep to the schedule, though. Can't go completely off track. Otherwise, we'll miss the coffee and we'll miss the lunch. So.
You mentioned that in 0.5% of the cases you would fail open completely. Is security less of a concern for that, or like what are? For our organization, we rely heavily on Envoy, Istio, etc. for security measures, but the whole fail open thing triggered a lot of questions for me.
Yeah, so for that 0.5%, those are actually connections that we find when we go in and debug into it that are just never succeeding. So it's like application A is trying to talk to B, the connection fails, so we try the fallback, and then that also fails. There is a very small rate, I think we see like on the order of like 10 connections per second across the fleet where we are failing back because of just some instability. We do log those, so for every instance of that, we have source IP, dest IP, and able to match that to workloads. And so eventually, we do want to move all of this to fail closed, at least by default. We want the controls to be in place to where we can fail things open. But for this rollout and for like in this initial onboarding, we want to default everything to fail open. Because that kind of gives us, in some sense, the leeway to roll this out and have issues happen, but not actually negatively impact the business. So later this year, we plan to do kind of another round of what we call production readiness review, where we take our previous kind of readiness model, which relies on fail open, and say, well, now if we're going to fail closed on things, like how does that change our risk? What additional controls do we have to put in place? How do we have to improve our operations? as well as just kind of demonstrating like, hey, we've been running this thing for a year now. This is how it actually works in production.
Thanks.
Hi. You did mention earlier that you saw quite a bit of CPU utilization on the TLS sessions. Have you done any work on the quantum ciphers and whether that impacted the CPU utilization more, or was it the same?
So I think the benchmark that we've done is ECDS that we use for signatures, and then RSA and AES that we use for the symmetric keys. We haven't looked at using different algorithms yet, since we have mixed fleet where we have AMD, ARM, and then x86 everywhere. So most of these processors have accelerated instruction set for AES, but we haven't investigated into the quantum algorithms yet. Yeah.
Cool. We could probably take one more question. Cool. In that case, thank you very much, guys.
Right. Thank you.
Thank you.